Friends, colleagues, ladies and gentlemen, it is my great pleasure to be able to present our research in this forum. My name is Swati Sharma and I'm a postdoctoral researcher at the University of Grenoble, Alpes. The research I present today is titled KDetect, Unsupervised Anomaly Detection for Cloud Systems based on Time Series Clustering. This work was done at the University of Grenoble, Alpes in collaboration with the French company Easyvirt. Clouds today run a large part of the IT infrastructure. They host a large number of virtual machines to the tune of several thousands. Each of these virtual machines, in turn, is running applications which are of unknown nature to the cloud provider. The analysis of these virtual machines needs to be done in a non-intrusive manner, which means that as little internal information about the user's data needs to be captured. Analysis is done typically by monitoring resource consumption metrics like CPU usage, memory, disk, and network. In this paper, we target periodic time series. Of the many applications, a very common example is an online backup service where after a specified amount of time, automatic backups from the user's data are taken and stored on an online backup server. Anomaly detection is thus very consequential for VM monitoring. As we can see from these sub-figures, anomalies are highlighted in red, which can take the shape of unexpected system behavior as compared to the past system behavior, or unexpected system load as compared to the general system load. Objectives of a good anomaly detection algorithm hence are generic solution to detect the anomalies, processing unlabeled time series, high accuracy, which means high recall and precision for anomaly detection, and quick execution of the algorithm. There are two main challenges in this. First is the large amount of data sizes, as we discussed. So the execution time per VM adds on for the large number of VMs, and the absence of labels for all this data makes the anomaly detection algorithm difficult to operate. Then the data content. We show two VMs here from our set of VMs, where blue shows the normal behavior and red shows the abnormal behavior. So each plot contains 3 days of data, out of which 2 days are normal and 1 day is abnormal. As we can see, there are diverse normal behaviors for each of the VMs. And also the changes or the differences between the normal and the abnormal behavior are very subtle, which render the traditional statistical approaches ineffective. Thus, we present KDetect, which is an unsupervised learning technique to detect anomalies for time series that exhibit periodic behavior. It is a dynamic partitional clustering based solution which provides generic heuristics without any configuration changes for the different services being run on different VMs. Evaluation of KDetect is done based on production dataset from Easyvirt. We see recall values of more than 94% and precision values of more than 95%. KDetect shows fast execution times. For instance, for a virtual machine which consists of 330 days of data, it is analyzed under 3 minutes. Anomaly detection is an actively researched subject for clouds. In this presentation, we refer to works that are directly related to our research. Agarwal in 2017 presented adaptive real-time anomaly detection, which analyzed nodes that ran similar services and predicted the next values to detect the outliers. Zhang in 2019 presented cross-dataset transfer learning for anomaly detection in cloud. This work is orthogonal to our solution as it learns the anomaly patterns from one cloud and transfers these patterns onto the next. For unsupervised anomaly detection for client time series, Zhu presented Donut in 2018. It is state-of-the-art anomaly detection algorithm which is unsupervised in nature and is based on variational autoencoders. We used this approach to compare the performance of KDetect. Paparizos in 2015 presented K-shape, which is an iterative refinement-based clustering algorithm which uses shape-based distance measure for comparison of the time series. Thus, positioning of these time series in Euclidean space is done based on the comparison of its shape, as shown in this subfigure, where the time series are shown in green and blue and the shape comparison process is shown with the black lines. K-shape has two main steps. First step is assignment, where the time series are assigned to different cluster centroids based on their shapes. And the second is refinement phase, where the cluster centroids are themselves refined based on the member time series. The only drawback of K-shape is that it requires the number of clusters to be known in advance. We use K-shape as a basic block for KDetect at every iteration for the creation of clusters. Thus, we present KDetect, which is an unsupervised iterative refinement-based clustering algorithm. It progressively increases the value of K, and at each K value, it clusters the time series into normal and abnormal. So the two main challenges that KDetect encounters are, first, how to decide which segregation or which K iteration provides a good differentiation into normal or abnormal time series. And second is how to label these clusters at every iteration as normal and abnormal. We describe this process with the help of an example. Here, and since it is before the KDetect starts its execution, so all the data is presented as a single cluster C1. We use shape-based positioning of the time series on the Euclidean space. So each point here represents a time series. A green point represents a normal time series and a red point represents an abnormal time series. As KDetect starts the execution at the very first iteration, the value of K is 2 and hence the data is divided into two clusters. KDetect assumes that the bigger cluster is the normal cluster and the smaller cluster is the abnormal cluster. As every iteration progresses, the value of K is incremented and the data is divided into K clusters. KDetect stops at a value of K which provides a good segregation of normal and abnormal time series. For this example, this value of K is 8, which has 5 normal clusters and 3 abnormal clusters, as we can see in this figure. The metrics that we use for cluster segregation are density and standard deviation. For the purpose of this presentation, we focus on density. Details about standard deviation can be found in our paper. Cluster density is defined as average distance between any two time series in the said cluster. This example shows the concept of density. Since density is an average of the distance between any two time points or any two time series in a cluster, it is basically a measure of degree of compactness or degree of similarity between the cluster. So closer the points are together, closer is their behavior and better is the density, and vice versa. In this subfigure, we show density as a function of the number of clusters. Instead of examining each of the iterations in detail, KDetect employs the concept of threshold, where the individual examination of the iterations is done after a threshold increase in density is seen. By threshold increase in density, we mean that the density increase of say X% is observed between two consecutive iterations, say I and I plus 1. So in this example, if we observe a threshold increase between iterations 8 and 9, and after iteration 9, an individual examination of the iterations is done till density increase is observed. The point at which the density increase stops is a good stopping point for KDetect. Another important point to see here is that because of the concept of threshold, we stop at a good local optimum, not the first local optimum. So the first challenge was to be able to determine what is a good segregation point. And the second challenge was to label each of the clusters at every iteration. At the first iteration, that is k is equal to 2, the data was divided into two clusters, C1 and C2, where the bigger cluster was assumed to be normal and the smaller one to be abnormal. So labeling at the second iteration, at the initial iteration, is very simple. Here we define a concept of beta. Beta is defined as twice the distance between any two time series in the initial normal cluster, which is the bigger cluster at the iteration k is equal to 2. This value of beta is used at every iteration henceforth to calculate the labels. We illustrate this with this example here. When the iteration, at the next iteration, k equal to 3, we have 3 clusters. So if, for instance, if we consider cluster C3, the label for cluster C3 will be determined based on the calculation of a distance value, which is the distance between any time series here in this cluster at iteration k equal to 3 and the time series in the initial normal cluster, that is the normal cluster at iteration k equal to 2. If this distance is more than the value of beta, then the cluster is labeled as abnormal, otherwise it is labeled as normal. The rationale here is that the Euclidean distance between the time series is based on the comparison of its shape. So larger is the distance, more is the difference in the shape of the time series or the behavior of the time series. So if the time series in this cluster C3 are very different from those in the initial normal cluster, then the behavior of this cluster is abnormal, otherwise it is normal. The evaluation of KDetect is done by 4 aspects: the performance statistics of KDetect, comparison with state-of-the-art approach, which is donor, analysis of the auto-stop criteria, and analysis of the execution time. The K-shape implementation we use is in Python 3, which is given by the tslearn library version 0.3.0. Experiments that are conducted are on the server have the configuration CPU, which is 12-core Intel Xeon, 48 GB RAM, and OS version is the Linux Server Edition Debian 4.9. The data is collected from the French company Easyvirt, and this production dataset consists of almost 2000 VMs. For the purpose of this presentation, we illustrate 4 VMs which exhibit diverse normal and diverse abnormal behavior and non-trivial differentiations between the normal and the abnormal behavior. Manual labeling of all this data is done by Easyvirt experts in order to evaluate the performance of KDetect. For each of the VM, we have about 300 days of data, and each day of data is divided into time windows of 10 minutes duration. Each 10-minute time window is averaged as one single point in the time series. So the 24-hour period can be exhibited as 144 points in the time series. The metric we use is the CPU consumption percentage, and the ratio of the normal to abnormal time series for each VM is about 3:1. In this table, we show the performance characteristics of KDetect. We refer to the 4 VMs as VM A, VM B, VM C, and VM D henceforth. We can see that with the exception of VM B, all the VMs show recall value of more than 94%, and with the exception of VM B, all the VMs show a precision value of more than 99%. We also see that the false positive rates are very low. For VMs A and D, this value is 0, and for VMs B and C, this value is 1.1 and 0.3 respectively. Donut implementation that we use is in Python 3 using TensorFlow 1.5.0, which has been provided by the Donut authors. Donut basically uses the reconstruction probability threshold, which determines whether a point is normal or abnormal, which by extension means whether a time series is normal or abnormal. In our case, for each VM, we test about 1000 threshold values between the lowest and the highest probability, and we use the value which shows the highest values of recall and precision. We divide the data into 60% training data and 40% testing data. The figure here shows the performance characteristic statistics of KDetect as opposed to Donut. The pink bars show the KDetect statistics and the gray bars show the Donut statistics. Also, the solid filled bars show the recall values and the dashed filled bars show the precision values. As we see for all the 4 VMs, in the best case, KDetect outperforms Donut in precision by about 48% and in recall by about 20%. The difference between these algorithms in precision and recall may be attributed to the fact that Donut determines any variation in the normal behavior as well as any noise which is seen in the system as abnormal behavior, which leads to a large amount of false positives. Next, we analyze the autostop criteria. As we had seen, VMB showed the lowest values of recall and precision, so we analyze VMB here. For VMB, the autostop iteration is k is equal to 7. So at k equal to 7, we see that this is a good local optimum. But the best local optimum is seen at k equal to 14. And there are quite a few iterations between these two, k equal to 7 and k equal to 14. So we see that there is an inherent trade-off between the execution time and the precision which is required for any application. Also, because of the use of threshold increase in density, we see that KDetect stops at a good local optimum and not the first local optimum, and hence we can say with certainty that KDetect selects a good value of k. This plot shows the execution time of KDetect as a function of the number of iterations k. Each value in this plot is an average of 10 executions, and we see that as the value of k increases, the execution time increases linearly. And this value is different for all the 4 VMs because the number of days is different for all the VMs. So the VM with the least number of days shows the fastest execution, and the VM with the maximum number of days shows the slowest execution time. This value of the execution time is represented here in the table. For VM A, B, C, and D, the autostop iteration for KDetect was 5, 7, 3, and 3. So the maximum number of value of the iteration is 7 for VM B, which takes about 172 seconds to execute, which is under 3 minutes. The values of execution time for the rest of the VMs are 100 for VM A, 63 for VM C, and 101 seconds for VMD respectively. In conclusion, we show that KDetect is an unsupervised learning algorithm to identify anomalies for time series that exhibit periodic behavior. It is a dynamic partitional clustering-based solution for clouds. It relies on generic heuristics, which can be applied to a large number of virtual machines. It is based on K-shape as a building block, and it uses multiple VM traces from production data for evaluation. We see that KDetect shows high values of precision and recall and low values of false positives and execution times. VMB showed us the least values of recall and precision. This could be attributed to errors like mixed clusters or mislabeled clusters. Thus, reinforcement learning could help improve such errors of mixed and mislabeled clusters and hence improve the recall and precision of the algorithm. Also, all the evaluations done till now were done in an offline fashion for data which has been collected in the past 24 hours or the past few months or the past year, which could be adapted to run in an online fashion so as to improve the lead time for anomaly detection. Thank you.